Good afternoon, everyone. Welcome to our student CSEC workshop. And this afternoon with me is my co-host, Kame Johnson Burrell. Kame, I'm going to ask you to
Good
greet
afternoon.
everyone.
Hi, guys. Are we ready to learn some math today? I'm sure we're going to have fun. So tune in, ensure that your ears are open and your eyes are definitely not closed because we are going to vector out some math today. All right, guys?
Okay, so this afternoon, we will be looking at vectors. And we would have shared that this afternoon's presentation will be done by myself, Mrs. Cameron Edwards, and Mrs. Johnson Borrell. So this afternoon, Camille, what are some of the things that our students this afternoon will need?
All right, so first up, we're definitely going to need our pencil. And we know as good mathematicians, we can't go anywhere without our calculators. We're going to need our ruler, notebook, and grid paper, but you may know your grid paper as graph sheets. So I think we're going to give them a couple seconds to hurry up, run, grab all these items that they're going to need and gear up for our session this afternoon.
All right, so students that are on the platform with us, make sure you have all of these. You're going to be talking with us. So we want you to understand this afternoon that in order for you to share your thoughts or comment, you're going to have to use the chat. However, if you have something that you want to say or ask a question and you are going to have to hold up your hand, use the raise hand icon. We will recognize who you are and then we'll allow you to speak. All right, so let us get the ball rolling, Camille. I heard all the enthusiasm in your voice. So I know this afternoon session is going to be a wonderful session. So, Camille, today as we're about to look at vectors, by the end of today's workshop, can we just speak to some of the things that the students should be able to do by this afternoon session?
Yes, we can. So one, we're going to be able to simplify expressions involving vectors. So we're going to look at addition, subtraction, scalar multiplication, and the triangle rule. We're also going to look at using vectors to solve problems in geometry. And when we talk about geometry, Mrs. Edwards, what are we really talking about here? Because we are hearing of vectors, but geometry, what we're really talking about here?
No, we're going to be reviewing things that they already know about parallel lines. We're going to bring in some new terms. So we're going to look at points on a straight line. We have a special name for that. And we're going to be looking at displacement. So certain geometric concepts that that are found in vectors, we are going to be exploring those today. So if you remember when we're talking about our parallelogram, what are some of the geometrical properties that you learned? Those are some of the things we're going to revisit this afternoon. So let us see if we can get into our session. So here we have our starter. So Camille, we have Marsha who is standing at the bus stop. Now, to avoid being hit by a car, Marsha ran 5 meters away from the bus stop. So, Camille, how do you think we could represent Marsha's movement based on this information?
Hmm. So I'm putting on my thinking cap now. So I'm pretending that I am Marshall. But I need you to draw. You're going to do a little sketch then of my description. And
All
we
right.
want the students at home to also try to do their sketch. So let's see. Marsha is at the bus stop. A car is coming straight to hit her. I would go to the right. Based on where Marsha is standing, I would draw a line going to the right. And then it's not just drawing a line. I want you to know that I am going to the right. So I'm going to put an arrowhead to show that I am definitely going to the right. But then guess what? I can't just be running to the right, not knowing how long I'm to run. And I know that Marsha is to run 5 meters. So there and then I am going to ensure I have 5 meters to show, okay, my direction is that I'm going to the right and my distance is 5 meters. Now for students who are home and you're watching us, wherever you are as well, you can type in the chat to let us know if you would have had something similar to what we have here or something different. So you can talk to us in the chat.
All right. So Camille, I'm seeing you're telling us something here based on your diagram. I see that you were quick to move and you decided to go to the right. So based on where Marsha is standing at the bus stop, we're seeing uh, a line segment and we see a arrowhead here indicating that you're moving to the right. I'm also seeing where you're telling me how far you actually ran to based on the car coming, and you would have gone a distance of 5 meters. So Camille, what if I decided that I wanted to go to the left? How could I actually represent this?
So I'm not going to the right, but I'm going to the left. So that means I'm still going to have a straight line and I'm going to go towards where the bus stop is now, to the left. But my arrowhead is now going to go to the left, representing that it's a different direction. But guess what? My distance does not change. I still need to run, or better yet, Marsha still needs to run away from the car 5 meters.
All right, so we have a different direction. Clearly, the blue arrowhead is indicating that I am not going to the right, I'm going to the left. And we're also seeing students that Marsha actually move 5 meters. So Camille, what can you really say to me as a reminder then for those persons who they're not so used to vectors, and even just as a reminder to the students to say what really is a vector?
Well, based on what we look at here with Marsha, we can safely say our vector here had a direction because we needed to know what was our direction, whether Marsha is going to the right, to the left, upwards, downwards. We need to know our direction.
All right.
Another thing is that we also need to know our distance. So we can look at it, vector, direction, distance.
All right. So you know what, Camille, I'm thinking that we need to go and check some of the things that the students already know about vectors. So students, what do you know already, or what is it that we are saying you should know about vectors? So the first thing here, Camille, it says that a vector is a quantity that has both magnitude and direction. And you notice that the word magnitude is in red as well as direction. But you didn't use the word magnitude, you gave me something else. What could I say? Give me another word I could use to speak of the magnitude.
Distance. So I would have used the term distance. So if we're listening, we need to listen for those key terms. So I would not have used magnitude. However, I used the term distance.
All right. And I know you were very direct in the direction you are going. You even told me to put an arrowhead there to indicate if you're going to the right or if we had changed our mind and decided to go left. So a vector then is a quantity that speaks of the length, the distance covered, which is what we call magnitude, and then the direction that we're going. So Camille, did you know that a vector can be represented or illustrated by these, by an arrow diagram or by a
Well,
column vector, which is what sometimes we'll call the column matrix, but we're going to be sticking with column vector.
Well, based on what we looked at with Marsha just now, and these are facts that we should already know. I mean, not have remembered just like some of our students, but now we are reminding ourselves that vectors can be represented using an arrow. And we're in our lesson further on, we're definitely going to be looking at what does the arrowhead really mean. We know that it means direction. So we're going to be looking at that. So with an arrow, the length of the vector represents the magnitude. The arrow, as I would have just said, indicates the direction of the vector. And here we have a column vector. Here we have 3, 1. Now, When you think of column, Mrs. Edwards, what comes to mind?
Well, when I think of column, I am looking at something that's vertical. And here right away, I'm realizing that we have two rows, but then we have only one. We have one set of numbers in one column. So from what I'm seeing here, a column vector is one that will have two rows and one column.
Good. So right
And
here
it
with our
also tells us, what is key here? I realize that you have a 3 at the base of the triangle. And I, earlier, I realized you told me to put 5 meters in the movement. So this we're going to see later. What is it the 3 really means as we talk about the distance move, and then in terms of the direction that we're going, and we're also going to talk about what the 1 represents. So, Kami, we is that the only way though that we can represent a vector?
not at all. And we're going to be looking at all the ordered pair here as you would have had it, or the column vector ways how we can represent our vectors here. So let's take a look at the different ways that we can represent vectors. So when I look at this, I'm seeing, in my first one, I'm seeing just A by itself. Then when I look, but I recognize here that my 3, 4, it's still in our column. When I look at the second vector, still 3, 4. But I realize that A has a little line above the top of the letter. The third one, no, the line, that little line there is not above A, but it's below or beneath A. My column vector does not change. But then when I look at the fourth one, I'm seeing a capital A, a capital B, and an arrow above my AB. Can you shed some light on this, Mrs. Edwards?
All right, so students, we want to hear from you in the chat. Let us know what is it you're observing? Is it that these are 4 different vectors, or are we just looking at the different ways in which, the various ways in which we can represent a vector? So let us see what the students are saying. So students, we're giving you 2 minutes or so to type in the chat which one of the vectors that you normally see when you're actually representing a vector, which one you have never seen before, and stuff like that. Because the truth is, Kami, sometimes we will see the common letter and it's bold in some books, or even when we're doing our research, but it still speaks to the same representation, the 3, 4. No, sometimes we may see the one with the accent above. And as you rightly said, the numbers are still the same. So these are all just various ways of writing a vector. Now, the last one for me, capital A and B. No, Kami. Unlike the others, these are actually 2 letters. No. How many of them probably will say, yes, this is the one I have seen. I see somebody lighting up the chat. Kami, can you tell us what is it they're responding to? Which one they say they would have seen before?
I'm not clearly seeing that on my side.
Okay.
All
All
right,
right.
hold
So
on, hold on. All right, so Gabriel Gray is saying, thank you, Gabriel. Normally, I would see the 2 capital letters with the arrow overhead and the common letter A with nothing over or below it. I've never seen the other 2, miss. So obviously, Gabriel is learning other ways of representing the vectors. Here, anybody else wants to share? Thank you, Gabriel.
thank you, Gabby. All right. So basically, what we're saying here is the the various ways that we can represent a vector is seen right here. I believe we can take one more.
No, you can continue, Mrs.
All
Edwards.
right.
You can
Thank
continue.
you. No, in their discussion, or in just as what Gabriel would have shared, we want to see if they truly understand. When earlier, when we saw the column vector, what is it that they really understand from that? So let's do this recap with them. So we have the vector A here. And Camille, we're going to look at exactly what is happening with this animation. What do you see happening, Camille? Students, type in the chat and tell us, what do you see? We see something happening here. What is it you're seeing?
Right, so I'm not seeing any responses as yet. So I'm still awaiting, not seeing. Come
All
on,
right.
guys. Come on. We know you know it already. Just tell us what it means. What does the 4 mean? Tell us what we're seeing happening here. Come on, guys. We know you can do it.
Well, I just see something pop up, Camille, and it's pointing to the 4, and I say 4 right. Let us see what happens again. I see 2 up coming, and I see that's pointing to the 2. So, Camille, if a student saw the column vector 4, 2, what kind of understanding would they need to either represent this vector or to have, in the back of their mind to say, all right, if I see the vector 4, 2, this is what it really means.
All right, so looking at our vector here, 4, 2, we are, and even looking at our representation here of vector A, we recognize that our 4 represents our horizontal movement. So it's 4 units to the right. And if we look at our arrowhead, we will see that it's going to the right. Now, when we take another look, we're recognizing that we go 2 units upwards, right? So it's 2 unit upwards. And I'm seeing Palette, Lindsay here, and Deja responding in the chat. Good. So it's 4 units, yes, 4 places on the X. So we're definitely not moving on the X axis or the Y axis, but we're actually moving parallel. So if this was a Cartesian plane, just as how you would have drawn it on your graph sheet with your x-axis, your y-axis, so it would have been 4 units to the right, parallel to your x-axis, and 2 units upwards, parallel to your y-axis.
All right.
Good. So
So
Terry and nice. So the responses are coming in quickly, Mrs. Edwards. It's popping up. I see that the understanding.
all right. So we also seen here on YouTube where students are commenting. All right. And I want to give a shout out to Antonia Brown. He says you're going 4 units to the right. All right. So awesome. I see this response is coming in. So Camille, you used that term earlier because sometimes when the students are seeing the vectors, they believe that they're actually moving on the x-axis. But I liked the way in which you are describing this movement. It was parallel to the x-axis, parallel to the y-axis if we actually had the Cartesian plane here. So students, what if I decided to go to the opposite direction with the x components? In what direction would I be going? If I say I wanted to go in the opposite direction, and how
Great.
would I represent that? I see the chat
So
lighting up.
yes, man, Gregory is saying he would go to the left.
And
Anybody else agreeing with Gregory, or are you disagreeing with Gregory? Talk to us.
all right, and I want to add to that. So if we're going to the left, Gregory, all right, how would I represent that? Anybody can tell us if we're going to the left, what would it be? 4, positive 4? What would it be? What do I use as an indication to say that I'm going left or I'm going right or I'm going up or I'm going down?
All right. So here we're seeing on YouTube, A said to the left, Chanel Gardner said to the left, and she also said 4, but A also added that it would be a negative 4. Chanel agreed negative. And looking here too, I'm seeing in our chat right here live as well, Karine on Zoom is negative 4. Gregory is saying the same. The arrow is going to point to the opposite direction from the origin right here. And I'm seeing again, Terrian is saying negative 4. So yes, students, you are correct.
Awesome. So, as we do the first part, which is just checking their prerequisite knowledge, we're liking what we're hearing. Students are preparing for the exam and we like it. All right. So those persons who have not yet shared either in the chat on Zoom or on YouTube, you'll get a chance to revisit the recording, the video, and you can go back and say, all right, what did they mean? Because sometimes we might not get the answer right away, but we can review and say, oh, this is what they were speaking about. So Camille, we're going to be moving on now to check if they remember some of these. So we're going to be talking about some types of vectors. And we have two types of vectors here. So we're checking again just to see how much information they know. The first one, Camille speaks about a free vector. Now, on the screen, we have a free vector PQ. Now, you notice that this vector is not coming from O, which is our origin. It can begin at any point. So one thing we want the students to remember is that when we are looking at free vectors, and know that we're looking at the Cartesian plane, we see our X and our Y axis there, or if it's even a grid, it can begin at any point. Now, Camille, I want you to check for me. If it is indeed that the vector PQ is actually 3, -1.
Yes, Mitty, it is indeed 3, -1.
All right, because as someone will have said earlier, someone mentioned that if we were going to the opposite of the positive 4, the opposite direction of positive 4, it would be -4. So, however, this one is still following the arrow. We are moving 3 units to the right and we're going down 1. So just to add us again that the movement which is parallel to the y-axis, we're going down. So that would represent a -1. So Camille, take us through now the position vector.
I went back in the chat because I remember one of our students speaking about the origin, that's
Yes.
Gregory. So Gregory Bryan, that is, pointed out about the origin. So here we are looking at position vectors. So the position vectors now all begin at the origin. And if we look here, we will see vector OP, vector OQ. These are position vectors, and we're sure you all, both on YouTube and in our chat here live on Zoom, we know you definitely know these. And you can also check if OP is correct, if vector OP is definitely correct. Let's look. So it's 1 unit to the right, parallel to our x-axis. Yes, that's correct. And it's 3 units upwards vertically. So we're going on the parallel to the y-axis now, vertically 3 units upwards. All right, guys? And it's the same for vector OQ. If we look at vector OQ, we recognize that we're going 4 units parallel to our x-axis, and we're going 2 units upwards parallel to our y-axis. We hope you all are good, and we hope you all are clear on these types of vectors.
All right. Thank you, Camille. All right. So I'm glad that you also pointed in terms of what Gregory had shared. I heard when you read his response as it relates to the position vector and being at the first, he didn't use the word position, but he did mention origin. All right. So no, earlier we had said something about the coordinates as well as how it is now that they look. So one more thing we want to review before we move from position vectors is that the point P on the grid is located at 1, 3. However, when we're writing it as a position vector OP, we're starting at the origin. It shows the movement that we are moving 1 unit to the right up 3. So another thing sometimes, or what we want the students to realize, is that the point itself speaks to the location of where Q is. For example, here we have Q is at 4, 2. However, the position vector now speaks to the movement. We're starting at the origin. We're moving 4 units parallel and to the x-axis, and we're going up 2 units parallel to the y-axis. All right, so this is something, again, we want the students to get. So Camille, we're going to now move on to another type of vectors, but I have a scenario for you. So Camille, suppose you walked from a point A to a point B, and I have it represented already on the screen. Now, if you were to walk back from B to A, would that be the same distance covered or distance traveled? And what is different? Talk to me.
Before
All
I
students, yes, go ahead.
Yes, so that's what I was going to say. So before I take a pick and answer, I want our students to tell us, would our distance here be the same? And tell us what would be different. So talk to us, guys.
All
All
right, so
right, so
suppose, yeah, go ahead, Kabi.
all right, so here I'm looking on YouTube and I'm seeing Joe Gamer, I hope I'm pronouncing your name right, is saying the direction would have changed. So he would have gone to the left. All right. So the direction would have changed. So he would have now gone to the left. I'm seeing Gabriel now saying here with us, same distance, but our direction would be different.
All right, so you think I should bring up our diagram?
Yes, man, let's show them. And here we have Virgo also saying the directions would change. So Virgo is also agreeing that our direction would definitely change.
All right, so we are now, so we walked, so the first scenario says that we walk from A to B, and we're representing that by using a small a. However, now we are walking back from B to A, and they said something. They said the arrow, so we are changing direction. But did anybody give us this minus A? Did anybody say that?
Not at all. Not at all. They only
So,
spoke about the directions would change, but no, nobody looked at that and pointed it out.
all right, so students, based on your observation here, what can you tell us then about two vectors? One go there of the same magnitude. You remember that word, same length. We cover the same distance. However, the directions are different. What can you pull from this? I see somebody quick, lighting up this chat already.
Yes, Tamika is saying she is looking at it from the opposite vectors angle. So
All right.
Tamika is saying, all right, Samantha is now saying one will be positive and one is negative. Tony and on YouTube is saying, yes, the distance would be the same, but it would be negative. AB, that's negative vector. AB, the vector AB would be negative instead of a positive vector AB. And Antonio is also saying, yes, but it's negative. So we're looking both at our YouTube viewers and we're also looking at what's happening here with us in Zoom as well.
All right. So I hear somebody saying that AB is negative. Now, what we want them to realize is that the distance or the vector itself, we use a common letter to also label the vector. So the vector, yes, is AB, but we use the common letter A. And when we're looking at the vector that is going in the opposite direction, as someone would have said, we are noticing that we have a minus a negative a representing that movement. Anybody else sharing something, Camille?
Yes. Not sharing, but it's just that it's what we would have been saying.
Okay, all right. So students, let's see what happens here. So the vector has the same magnitude. So the return journey, so AB, which is represented by small a, and the vector BA. So notice now I'm not calling it AB, but I'm calling the vector based on the direction in which I'm going. I'm starting at B and I'm going towards A in that direction. So, but the distance, the magnitude is the same. So though they might be going in different direction, we realize that their magnitude is the same. Next thing. So somebody brought it out, yes, opposite direction, and we can write it as this, because someone mentioned this earlier. So yes, minus the vector negative AB, yes, we spoke about that, or minus A, yes. Now, what if A was actually 4, 2? Then minus A is the negative of the vector A, which is the minus on the outside, 4, 2. You notice it is saying that this is the same as negative 4, negative 2. Why is this coming? Why would the minus in front of the vector 4, 2 the same thing as negative 4, negative 2?
Anybody cares to add before I answer? And guys, we are going to turn off our cameras a bit, both Mrs. Edwards and myself, because we recognize that you are not able to see the slides properly. So we're going to turn our cameras off. So we're still here with you alive and well, but we're just turning off our camera so you're able to see. All right, so so Tamika is responding to say the minus before the brackets indicate that everything is negative. Gregory is also adding the minus sign is for both values in the bracket.
All right, I've seen someone else speaking about equal vectors. All right, but guess what? You see, this type of vector that we're talking about, Kabi, is inverse vectors. Now, students, what are we able to take away from the heading here? What are we going to pull away from these two vectors, the vector AB and the vector BA? We know that they're inverse vector, but what did we speak of here? What are give me two things that we spoke about here before we move on.
I think Tamika would have added it earlier because Tamika, she didn't use the term inverse, but Tamika would have looked at it in the direction point of view to say they're opposite vectors. So they are definitely going in different directions. So guys, apart from the different directions, what can we conclude here based on what Mrs. Cameron Edwards just said? So yes, we looked at the directions being different when we look at inverse vectors. But what can we say? Remember, we had asked you a question. What is the same? What is different? What is the same? So think about it. 5 seconds. What's the same? What's the same? No, man, look at the two vectors that we have here. So we have one vector going in. Yes, right. So Tamika is saying the distance traveled is the same. Gregory is saying change from positive. So Gregory, it's inverse. Not sure if this is exactly what you're asking, but we're looking at inverse vectors here. So when we're looking at inverse vectors, what we're trying to conclude here to say is that, all right, when we look at inverse vectors, the distance of both vectors are the same, but our direction changes. And Virgo is asking, what is the difference with the arrow being in the middle? Oh, Virgo is responding to say what is different is that the arrow is actually in the middle, so it's showing a change in direction. Yes. So we can definitely conclude, as I would have shared earlier, the directions are different. Our direction here is different, but our distance is the same. It remains the same. And we have it here that our magnitude, which we would have shared earlier, magnitude is the same as distance.
All right. So thank you, students, both in the chat and on YouTube. All right. So let's also now see if that same knowledge or the information shared or discussed a while ago, they can apply it here. Now we have two vectors, vector AB and vector CD. Can you tell us what is your observation for vector AB and vector CD?
So come
Come
on, guys.
students, yes.
Both on YouTube and here on
Just type
Zoom.
it in
Tell
the
us.
chat quickly.
All right, so we're seeing Tonian on YouTube saying the magnitude is the same. You're sure, Tonian? Double check. Gregory saying they're parallel to each other. Why you say they're parallel, Gregory? Kelsey is saying they're parallel. Tamika is saying they're both parallel, but CB is twice the size as AB. Priscilla is also saying they're parallel. Let's look. Woo. So Gabriel now is saying vector CD is twice the length of vector AB. Deja is saying different magnitude. Karine, different magnitude. Desmond, same directions. Good. So we realize that we are looking at what is happening. Samantha, AB is half of CD. iPhone is saying CD is a scalar multiple of AD. Check that again for me, iPhone. Karine,
So,
same direction and they're parallel. So guys, we're seeing your comments. Good job. Yes, Mrs. Cameron Edwards, you can continue.
so for the students that's earlier, just identify vector AB and BA with the same. So, you know, we were pulling from inverse vectors there. And then they said it was equal. So I did hear one student share that the two vectors are parallel and equal. So, but I heard other students giving us that vector AB is a half of vector CD. I would like them to tell us how they came up with that answer. How did they come up with that answer?
Yes, they can. And for those who are not so clear as yet, I'm still seeing the responses coming in. So while you're answering Mrs. Cameron Edwards' question, how do you know that AB is half of CD? Tell us how you know that. So you're going to have to talk to us now. So send it in the chat. We are able to see. So you can send it. All right. So Samantha is saying, Miss, AB was 3-2 and CD is 6-4. Very interesting. We're realizing here that our students are really doing good observations.
Yes,
Gabrielle is
they are.
saying the point that is in the center of CD in interesting. Gabrielle is saying, Miss, I just look at the point. So I'm seeing a point in CD. So Gabrielle is really doing some good observation.
I realize. I realize. All right. So, students, one thing we wanted to have would have shared already is that the vector AB and the vector CD are parallel to each other. So clearly, we are seeing that they're both going in the same direction. Now we realize that some persons shared that. I think one person just shared that this vector AB is 3-2, and another, or is that same individual would have shared that the other vector CD is, what did they say? I think 6-4.
Yes,
All right.
yes.
So here's my next question. How would you write the vector A, B, and C, D as column vector? But guess what? There's a bright Mrs. Johnson Burrell that they already gave us the answer.
Yes, they did. It's just that. But look at it. They didn't give us the full answer. Something is
Exactly.
wrong. All
Exactly.
right. But guess what, too? They wouldn't have been able to do the column here, neither on YouTube nor in Zoom. But just to point out, too, that our students on YouTube, they're also responding because they're getting it right. Amelia, Antonio, they're definitely getting there and they're on point here. So guys, we want you to look carefully. Look at vector AB and vector CD. Now, you would have shared that it was 3-2 and 6-4, but take a look at the vertical movement. So remember, our arrow actually tells us the direction that we're going in. So we're moving from A to B. So when we're moving from A to B here, we would be going downwards. Great, which is parallel to the y-axis. Same thing with CD. We're definitely going to be moving horizontal movement first, parallel to the y-axis, and then our vertical movement parallel to the y-axis. So x-axis parallel to the x-axis, and then parallel to the y-axis. So remember our downwards movement, and we spoke about this. Yes, Tamika, it's definitely going to be negative because we are going down. Thank you, Samantha.
All right. So my final question on this then, student, is there a relationship then between the column vector AB and the vector CD?
And they would have shared this with us already, because some would have been saying, Miss, AB is half of CD, while some would have been saying CD is twice of vector AB. So vector CD is twice that of vector AB. So good job, guys. I'm giving you a virtual clap. All right, guys? Good job.
And the key thing here, Mrs. Johnson Burrell, is that these were their own observation, because just by giving them the two vectors and asking them what did they observe, they brought out that they're parallel. They were able to give us, for some, the correct column vector. We addressed the down movement, and they were already telling us that CD is twice that of AB, or AB is half that of CD. Great job, students. So let's move on quickly. And we just wanted to show you just some key takeaway to this activity. So vector CD is a multiple of AB. And as we give you these, we use these words and we try to coin the phrases and the statements for you in your preparation to answer questions. You may be wondering how it is I can answer the relationship. In answering the question that speaks to relationship, you may want to use words as we would have shared twice, half, and now we're adding something to what you would have shared, that the vector CD is a multiple of the vector AB. Now, this actually means that they have the same direction. However, who remember factorization? Who remember factorization in algebra? Can we factor 6 negative 4? So that it looks something like 3 negative 2.
All right. So I wish iPhone, I'm not sure if you're able, iPhone 31, to rename yourself, but I would love to call you by your name, because iPhone 31 said CD equals 2AB.
So CD is going somewhere. So CD is factoring 2. All right, so very good. So students, so sometimes you'll see the CSEC questions asking you about a relationship, geometric properties or geometric relationship. These are some of the things we want to look out for. We want to see how two vectors, if they're parallel, is one a multiple of or factor of. So these are terms we want you to also remember, make sure you're making a note of these, because guess what? Mrs. Johnson Burrell told us very early that we will need our notebooks, we will need our pen, we need our grid paper, graph paper, as we rightly call it, as we are going through today's workshop. All right, very good, students. And I like that Mrs. Burrell gave you all your virtual accolades. She a big one up over there. So this is now all yours. Now, can you identify the relationship among these vectors? We have some vectors here. I want you to now tell us, what are you observing? So we now want you to share with us on YouTube, share with us in the chat. What is the relationship you observe about these vectors, as well as how would you represent the vector CD, the vector EF, the vector GH as column vectors? So we're giving you like 10 minutes or so. Come on, students, get out your books and your pencils and start writing down and then share your observations. All right, we have some
Right.
people on the ball.
Yes, Tamika is saying, and just as how Tamika would have put it, Tamika, I want you to fix up that word opposite for us and fix it up and tell us what word, what term you used and we used for opposite vectors earlier. So I want you to fix that up for us, Tamika. So here Tamika started off with she's good. All right, Samantha is helping Tamika by saying in great Tamika inverse vectors, but you have to tell us which ones. So we love that you're telling us that okay, miss, we're seeing inverse and we're seeing maybe parallel and we're seeing this, but we want you to talk to us, man. Be specific in the messages. So Kuala is saying GH, so vector GH is the inverse of vector AB. All right. And then I think it's Tamika now is saying vector AB. Yes, so she would have been saying the same thing as Kuala. Anybody else has anything else to add? All right, so Gregory is saying vector EF, CD, AB, and vector K. Great. So I'm happy that somebody recognizing that we have a K by itself up top are all going in the same direction. Good. Samantha, vector EF is half of CD. Great. Anybody else wants to share before we carry on? Anybody else? Let me check YouTube to see if we're bubbling in YouTube as well. Great. So Tony Ann on YouTube is saying AB is half of CD. Great. I think this would have been AB is half of, all right, so this one would have been from the first response. All right, Tonian. So Antonio is saying, okay, miss, it is half right here. All right, but guys, we have to be very specific.
Yes.
K
So,
is equal to 2EF. All right, good. So we're going to be carrying on because you recognize that you know what you're doing. So we're going to be looking at the relationships now, just concretizing that, okay, we do have inverse vectors here. You are indeed correct when you said vector AB and vector GH are inverse vectors. You were definitely correct.
all right. So we realize that the students are actively participating and they're giving us some good information. So as it relates to the specific one, now let us go through those quickly. So we're looking at CD, and we are now here asked to in terms to share the column vector. And even though we did not say use the key as the vector K as the benchmark, vector K, clearly if you would have realized that vector AB was renamed to 2K, which means that the vector K is what we're using as the benchmark here. The vector CD is also 1.5K. The vector F is half K, and I like how several students shared that GH, you notice the arrow that the direction is changing and it is negative 2K. So students, the vector CD, how would I represent that column vector? How could we represent that column vector quickly? We need the responses quickly. We're going to
I'm not
just take a
seeing
few.
responses yet. All right, no problem.
All right, so Camille, let us see if we can see what will happen here as we compare CD to the vector K. All right, so we are going to see that it's K plus half K. Now, how would we write that?
Let's take a look at how we would write.
All right, so we see K or 1, and then we have a half, so it's 1.5K. Now let us actually check by counting. We are moving 3 units to the right, 3 units up. So indeed, the vector CD can either be represented in terms of K, or we can also represent it in terms of the column vector. Now, students, how would you tell me, or what would be EF? Talk to me. Anybody want to tell me what the vector EF would be?
So that's the coordinates Mrs. asking.
The column vector
Yes,
itself.
the color. All right. So someone is saying 1, 1. So EF 1 is 1, 1.
All right, so we can use the diagram to tell us. We are seeing it here, but let's look at how we would work that. So students, because we are doing some scalar multiplication here. So if the vector k is 2, 2, a half of 2, 2 will give us 1, 1. So even though we're not literally seeing, we wanted to understand that this is a scalar multiplication of a half to the vector k. What about GH? What can they tell us now about the vector GH?
Let
It's
me
2, negative 2 times the vector k. All right, so let's look back quickly. If vector k is 2, 2, and we are multiplying that by negative 2, what would our answer be?
All
All
right, so
right.
Gabriel is saying negative 4, negative 4, Deja, negative 4, negative 4. All right. And I believe Ruhama, I think on YouTube, she would have been close to it, but something is a little bit off. Your horizontal movement parallel to the x-axis is a little bit off, should have been negative 4. Jodian is also saying negative 4, negative 4. Montana, you want to double check that?
All right, so
Kadian, double check as well. Yes, miss, continue.
So you know what we want the students to see here, Camille, that sometimes a relationship can also be expressed in terms of a common letter or in terms of K or any other letter A or B. So when we are now going to explore vector addition and resultant vectors, and they may not see 1, 1, like how the vector EF here is 1, 1, or they may not see negative 4, negative 4, but they should also understand that as we move into some vector algebra, that they're going to be doing some multiplication of scalar factors to arrive at vectors as well. So very good activity, students. Would like a participation. All right, we're going to move on quickly. So this question is now yours. Now in the diagram, now the diagram here below is not drawn to scale, but it shows a quadrilateral ABCD. Now right away, as you see the word quadrilateral, you begin to process and say, all right, what do I know about a quadrilateral? And does this is this actually a quadrilateral? But they're giving us something specific. Notice here we have this as a sample question. So the vector AB is equal to M, and the vector DC is equal to 3M. So we have the diagram here, the quadrilateral. So these are the questions we're asking. Complete the statement below on the geometric properties of the following vector. So what can we say? The vector AB and DC are, and when you say what it is, you have to tell us why. And then we're going to also talk about the second one, but I want to hear your response to the first one. I see something happening.
Yes, yes, yes. Gregory, Davia. All right, so let me just call everybody one time. So Davia, Gabriel, Gregory, Deja, Samantha, Tamika, they are all saying, as well as Davia. Yes, I would have said Davia before. They are parallel. So here they're saying they are parallel, and Tamika is saying AB is parallel, and both vectors AB and DC are parallel to each other because they run in the same direction. All right.
All right. Is there any way, and is there anything else that we could describe it to say in terms of when we were talking about factor or anything? What else can we say?
All
Any
right.
other
So
geometric property? We heard parallel,
all
yes.
right. Amanda is saying they do not touch. Kadian on YouTube, and Cox, as well as Katie still is also saying parallel. But look, guys, and tell us, look at AB. vector AB and look at vector DC. All right, Davia is now saying scalar multiples. Davia, tell us what you're talking about here when you say
I hear the
scalar multiples.
excitement in Camille's voice. All
Yes, come
right, go
on,
ahead.
Davia, talk to us. Scalar multiples. So tell us what would you say then? So, all right, fine. Which one is really a scalar multiple? All right. So Davia is saying, Miss, AB is 1/3 of DC. Oh my
I
God.
like
Yes,
that. I love it.
Davia.
Love it.
Yes, she's on the ball. What else? So can we turn it around what Davia said then? So AB is 1/3 of DC. What can we say now about DC in comparison to AB? All right, Samantha. So Samantha is saying DC as well as Gabrielle is 3 times AB. Oh, yes. Oh, good job, guys. Yes.
Yes, Camille, I'm loving it. I'm loving it. But you know what we want the students to pull from here is that they are describing or they're sharing based on the quadrilateral, like based on the diagram given, they're simply giving us the geometric properties. So though they're parallel, we can also pull some more information from it. And you know that information can be completed in the next sentence or the next line. Now, here is something that they probably would not have seen before. You notice that we have a modulus, we have AB, and we have two vertical lines there, and we see is blank times, again, we have DC with two vertical lines. Now, we want you to understand that that's the representation of magnitude, and we're talking about the length. And rightly said, you would have shared that AB is 1/3, or the DC is 3 times, and so forth. So here are the things, and it doesn't matter the way in which you share. So the first thing we want to agree with you is that the vector AB and the vector DC is actually indeed parallel. And the vector AB is 1/3. So we like the fact that if it is talking about AB in terms of DC, it would be AB that is 1/3 DC. But I believe Gabriel and another set of students can may correct me, said that DC is actually 3 times the length or the magnitude of AB. So that's very good, students. So a lot of things came out here, and we're going to move on because we're going to now quickly go into vector, looking at addition and subtraction of vectors. Now, when we talk about addition and subtraction of vectors, you know, certain things like certain terms like resultant vector is going to come out, and we're going to get into that right away. So here we have the resultant vector. Camille, we have a vector AB that looks like it's going north. And then we have another vector BC that is connecting to so you know, I see a head and a tail kind of thing. And we're seeing the resultant vector there in C. Now, students, I'm not sure if this is the first time you're hearing this term, but let us see. So based on the diagram shows a displacement of a propeller plane caused by the thrust of the wind. So let's say we have a plane here traveling, and there was a thrust of wind against the propeller and some kind of shift. You know, the plane kind of did some movement, but some resultant is left. Students, how do you think I could end up with the vector C? How could I end up with AC? We're going to give them a little time, Kame, to look at this. How could I end up with that resultant vector C?
Come on, guys, look at it. Look at vector AB, look at vector BC. And if you look at vector AB, you'll see that we have a common A in red representing vector AB. If you look at vector BC, you'll also see we have a common B in blue representing BC. And then you see we have another vector, the resultant vector, and it's in green. So talk to us. Wow. Come on. No, man. I think we need to just end class right here because we
Them
have
bright don't. No,
geniuses. Yeah,
man. We have some bright children here this
yes,
afternoon.
man.
All right. So
So
students,
Gabriel is saying AB plus BC equals AC. Davia is saying add AB and BC. Oh guys, oh yes,
I
man,
think they saw our
Tamika.
presentation and they know what is coming next. Students, I think you peep into what we are sharing this afternoon. So let's look. So they're describing what they are seeing here. And as rightly, they were saying the vector AB plus the vector BC is equal to the vector AC. But we want to move it a little bit further to say if I represent the vector AB by the common letter A and the vector BC by B, and then the resultant as C, then we could have that statement. I want,
Yes.
go
And
ahead.
Montana on YouTube said it, you know. She said common A plus common B gives us common C. So yes, Montana, you are on target. Yes,
I
Miss
love
B.
it. I love it. So, students, what we wanted to take away here now as we talk about the resultant vector, that it is a vector resulting from adding two or more vectors together. For example, and you notice how here we have A with the accent below plus B with the accent below, because sometimes while I have it here on the PowerPoint, you can see that it's bold. So sometimes you'll see the accent below the letters so that you know that you're representing a vector. So sometimes you don't see it, but sometimes it's there. So basically, the resultant students, for those who would have shared so nicely, is from adding two or more vectors together. So we're going to be taking you now through a few vectors that we're going to say add. We're going to see the resultant, and we're going into some fun stuff now. Don't tune out, students. Those who are coming on, keep coming on. I hope persons are coming on the YouTube. It's going to be there, but join us and be a part of this session because we have another hour or so to go. Fun stuff. No, Kami, as was described a while ago, notice here we have the addition method. So we're going to be looking at aligning the head of one vector to the tail of the other, and we're going to give them some steps. But before we get to the steps, I want them to realize that the starting point and the end is right at the tip of the starting point to the other, and it shows the movement. So we want to
Yes.
leave this tip with them as it relates to aligning the head of one vector to the tail of another. So when we're talking about the addition of vectors, here are some tips we want to share with you. Kami.
All right. So even when we're looking at the tips here, guys, we want you to really look at the image that we have to see if it's really so it go. All right, guys. So one, place the tail of the second vector at the tip of the first vector. Two, go again now, miss. Draw in the resultant. That's the sum. Tail at the origin, tip at the tip of the second vector. So if you look at it, you'll see here that we have the head of one vector being aligned to the tail of another vector. And then when you look at it, you realize that we have our resultant vector taking place where we will have A plus B. So it's very similar to what we would have just shared in our previous slide and our previous image. We're just now formalizing it a little bit better for those. So for those of you who want to screenshot or you want to take a photo of what we have here, you can go right ahead.
All right. So, students, we know that you're learning. We can see based on the messages coming in that you're excited. We're giving you 2 minutes to just take off the information. All right. So we're gonna move on now to the triangular law. Now, suppose we wanted to add these two vectors, students. I don't know how many you might want to make a sketch in your book. I'm not showing you what we have in a copy. We are not going to show them because we don't want them to look over on what we have, right? So we are giving them the time to know, show us how they would combine. We gave them the hint a while ago, the head to the tail. We're connecting some things. We want them to know, show us first, draw it in your books and tell us how would you add to get the resultant of these two vectors.
Come on, guys. We know you can do it. Come on, try, man. Just attempt. Try.
It doesn't
Let
have to, it just needs to be something that's sketching. Come here, we don't want them sitting down there trying to fancy up the diagram. All right. So I believe a few of them probably they're drawing, but based on our time, we have to make sure that we move on. And I see one person probably indicating. So let's see what if they came up with what we have. All right. Did anybody come up with anything like this? Can just raise your hand and say yes.
or you can, all right. So Gabrielle is typing in the chat to say yes, miss. And
All
Tamika is
right.
also saying yes. Anybody on YouTube arrived at anything like this? All right, Karine, good job. Anybody else?
No, I want them to also tell us what kind of shape are they seeing here? What shape is this?
So when we look at geometry, remember one of our objectives earlier was that we're using vectors in oh my god, before I even finish talking, look at oh my guys, you are on the ball. You're rolling. Tamika, Ashley, Deja, Shamar, Davia, Carter, Aaliyah, Kareen, Samantha, Gabrielle. No, man, guys, you're good. Gregory, Tamika. Yes, man, I've seen all of it. I am seeing all of it, and you are all definitely correct. Yes, Delani from YouTube. Yeah, man, I seen it. Katie, yes, Cox, I seen it. Good job, guys. Yes,
All
Paulette.
right.
Come
So
on, they're all getting it, miss. They're
all
all
right,
getting
very
it.
good. So what we want them to understand here is that we just formed a triangle, which is what we call the triangular law, the triangular addition rule as it relates to two vectors. So we're using the head and tail and we're connecting the vector A with vector B, and the resultant gives us what we call a triangle. Now, students, is that the only way we could have drawn this? What if I had connected A to the, say, the tail of B? All right, let me see if I can bring up that image. What if I had connected it the other way? Would I have gotten the same result if I had decided to go with B first and then, so let's say I was to, let me put in my light. What if I was to lift this A and put it at the other end of B, starting with B first? So let's look at how we're going. We're going from B in this direction, and then we're connecting vector A to it. We're still completing our triangle. Now, my question to you, would we have the same result if I'm adding B plus A? Would we get the same result?
Oh my, Aliyah is saying definitely we would get the same result because no, she's looking and she's telling us a different type of shape, no one a different type of law. She's talking about the parallelogram law.
All right.
All right,
So
guys.
you know that she's well advanced in this class, but
Yeah.
we like it.
No
So
worry yourself, Christina is on target. Karin, yes, man, show us that you know it. Yes, they're talking to us.
all right, so what we can see here is that even if we decided to add B to A first, and as we move further into the algebra aspect of vectors, which I want the students to realize that a lot of the times you'll see the algebra, or you'll see the letters in the vectors. And sometimes students, they want to shy away from those questions. But I want to tell you the truth. If you do begin to understand what the question is saying, if it makes sense of the problem and you try to persevere in it and try and say, all right, this doesn't align to what I learned and do, then you'll eventually get it. So yes, but my final question to you here, can you identify any parallel vectors? And if you say yes, you'll have to tell me which vectors are parallel and I will just point to it. Anybody?
So guys, remember you can type it in the chat and don't go sleeping on us. All right, Gabriel. Yeah, to tell we know Gabriel and Samantha. We know you identify them, man. So tell us. So Gabriel is saying vectors A on the left and vector A on the right. All right.
All right, so
Great.
they are parallel. Good.
All right, Aliyah is saying B plus A and A plus B. Samantha is joining her. Anthony is joining her. Gregory, same thing. Oh my God, these students are brilliant.
So we are recognizing here that even though B comes before A, it still could have been written as A plus B when we look at the commutative law. All right. So wonderful. Excellent. We're moving on nicely. So here is your job. How it is that you would now combine. So we're looking at a simple combination here. We have the vector AB, which is 4, 1, and the vector BC, which is 1, 3. We want you to now quickly combine these vectors. We already have the drawing for you, so we want to tell us what would the resultant be and how did you come up with the resultant?
All right, Carter is on target. All right, Carter, I'm seeing your response. Anybody else wants to share apart from Carter? Come on, guys. All right, Antonio, you can share, man. Just type it in the chat. All right, Davia. All right, Davia, senior. All right, so they're on target. Davia, Samantha, Anthony, TB. They're saying by adding this, we just need to add. We just learned about resultant vector. So we add both vectors, right, guys? Good.
All right, so let's see what comes up. So we're looking at AB plus BC. Did anybody give it to us like this? Perhaps not necessarily so, but this is now something new we want to add. We notice here that we're adding the X components and we're adding the Y components. All right, so when we add 4 plus
4
1,
plus
we are
1,
going to
yes.
get 5.
5.
Thank you. And then when we add 1 plus 3, we're going to get 4. So the resultant AC then is 5, 4. And a number of you would have shared this before. Awesome.
Great job, guys. And Paulette is adding to that, miss. I added my X, my horizontal movement. She's saying X and Y. So the 4 and the 1 would have been the movement parallel to the X axis. Good job, Paulette. So she's still linking it to how we started off with vectors. And the 1 and the 3 would have been the vertical movement parallel to the Y axis. Yes, Montana and Ultimate and Kadian and Ashania. We're seeing your responses on YouTube as well. Good job, guys.
All right, so you know what is going to happen now, Mrs. Johnson Burrell, is that we're going to give them 1 on their own. So if the vector A is equal to 4, 2, and the vector B is equal to 1, 3, we want you to show that A plus B, 1, is an addition of the column vector. And then we're going to ask you to do something else, but I want you to first show us what A plus B would result in. And I just want you to put the answer there and let us know.
Remember too, we had said at the start of our session today that you're going to need your graph sheets or if you have grid papers. So we also want, apart from you doing your addition here, we know it's going to come up shortly. We want for you, for those who are finished, because we realize that we have some quick thinkers here. So our second question is going to be for you to basically do a sketch. So do it on your grid paper, your graph sheet, if you have it nearby. Look if you definitely get the same answer. So type in the chat if you tried it that way as well and let us know. Okay, miss, yes, it worked for me. No, miss, it didn't work at all. But we're seeing the responses coming in, miss.
All right, so
Samoya,
we
Sharnia.
can reveal then.
Yes, we can reveal.
All right, so for the first one, we have 4 plus 1, that's 5, and then 2 plus 3, that's 5. So our addition here, we'll add right, miss? We'll add right. So
Yes.
here's my second one, which I guess you already told them read the grid paper or the graph paper.
Yes.
We would like you to now represent this on the grid paper, on your graph paper. Now we want you to now show that A plus B using the triangular law of vector addition. Remember, we just spoke about the triangular law. We want to see how you would draw this and that you will add them using the grid paper or your graph sheet. All right. We won't be able to see your graph paper. However, we have a diagram coming up. What you can share is if you got the same diagram that we got. All right. So giving you 2 minutes. And with 2 minutes short, this is an estimated 2 minutes.
Very, very short. Even though we're mathematicians, we are very, very short with our 2 minutes this afternoon.
Yes, we are.
Precious 2 minutes, Mrs. Edwards. Precious to
Precious
us.
indeed.
So anybody wants to type in the chat that yes, you tried it? No, miss, I didn't get to try it. Anybody wants to tell us? Did you try it? Guys, come on. Don't fall asleep on us now.
Yeah, we don't want no sleeping over here. Come on now. It's probably because the camera closing on them not seeing how our face lighting up with all this excitement.
So come on, guys, you can do it. Yes. I hope they saw me just now.
All right. So let's see if this is what you actually had, students. So we're about to share. So let us know if your vector A looks like that. 4 units to the right, up 2 units. All right. And then we're going to look at vector B, which is 1 unit to the right, up 3 units. So what would my resultant be? How can I complete the triangle here so that I am using the triangle law of vector addition to show A plus B? Because that is what we are doing, We are showing A plus B. All right. Did
Oh,
we come
hold
up with
on.
this?
Hold on.
Yes.
That is saying before we showed it, Miss, let me see if they can see. Miss, connect A to B. So connect vector A to vector B and Shamar. Stop laugh at us. Stop the laughing, Shamar. And Ali, I saying, Miss, I tried it. And it was indeed successful. Yes, guys. Thumbs up, thumbs up.
All right. Nice. So therefore we would have seen or would have had something similar to this. We'd have drawn it. And when we are showing A plus B. So you know what I want to check now? Students, can we check based on our graph or diagram here if our resultant A plus B is actually 5, 5? So I am taking out my little spotlight thing and they're saying that they did it. So I'm going to check. So I go across. What is this? 5 units. And then
5 units parallel to our X.
yes, and I'm going up 5. So guess what? It's right, students. So if this is what you had, when we checked by counting and the different movements, we realized that indeed we ended up with 5, 5. All right. Session nice, Mr. Session nice, bad.
Yeah, man, I think they're enjoying it. I think they're having fun, especially Shamar. Shamar, he's
Shamar is having fun.
yes, man,
All
Shamar laughing.
right.
Good job. You're welcome,
Okay.
Tamika.
All right. Welcome. So, students, vector subtraction. Now, here I have a statement that's saying subtracting a vector is the same as adding its negative. Now, look at that statement. Now, what do you think we mean here, students? If I say that subtracting a vector is the same as adding its negative, what do I mean? What do we mean?
Guys, come on. So let me show you now. This is me now. Really, guys? Come on, man. You're doing so great. Okay. All right. So let me turn off but my camera because I want to ensure that we're able to see. So Alia is saying, Miss, what is this? Alia is saying inverse property. Uh,
Okay.
Carter is saying, Miss, negative plus negative is equal to interesting, Carter. Very. Tamika is saying, Miss, right here, no, it's going to cancel out itself. No, man. I'm happy that we're getting responses that are we're getting a variety of responses here. But even though we're getting a variety of responses, watch here. Christina came up with something similar like what we have, Miss. When you
Right?
add plus and negative, it equals interesting, Gabrielle. Interesting. Carry on, Miss. Carry on.
All right. So, students, what we wanted to pull here is that when we are subtracting numbers, or even here we're talking about vector, it's the same thing as adding its negative. For example, if I have, and I'm just going to use numbers now, if I have 10 and I want to take 3 from it, it's the same thing as saying 10 plus negative 3. So that's what the statement is saying. The vector u take v is defined to be the same thing as the vector u plus what? The inverse or the negative of vector b. So Mrs. Burrell,
I
you
think
mean
they
so
got
when
it.
we are subtracting vectors, I don't have to think about subtraction.
No,
All I
you know,
have to do,
it's just add the
yes.
opposite. So you add it. So you just add the opposite.
Okay.
So that's all you're doing. And I realized that, hey, they would have understood it too. I think they understand it. They understand. So if we're subtracting vectors, it's the same as if we're adding.
All right.
It's
So
the same.
here we have. So the difference, what you're saying to me, Mrs. Johnson Burrell, is that the difference of the vectors u and v, students here, the difference mean that we are finding, we are subtracting. So the difference of the vectors u and v is really the sum of u. And as you rightly said, the opposite of v or the inverse or the negative is the same thing. So let us now look at another case. Earlier, we gave you the addition and we looked at the triangle law of vectors and all of that. So here we want to subtract two vectors. So we want to subtract vector v from the vector u. Students, tell us, what do you think our diagram will look like, and how could we use what we would have learned already just a while ago about adding the inverse? How would that look? Talk to us quickly.
Let me check our fans on YouTube because we have fans on Zoom and we have, oh, Davia. All right, Davia. I'll soon let them know your response, Davia. Montana, yes, Montana is saying, Miss, I'm enjoying this lesson. Okay, Montana, kudos to you. All right.
All
Alia,
right.
Alia, something is missing. Come on, Alia. I know you can do it. Come on, Alia. But let me just share what Davia was saying and Gabriel. They're saying
All right.
U plus open bracket negative V. Alia is saying so it's negative V plus U. Samoya is saying U plus negative V. Interesting, Miss. Interesting.
All right. I like the fact that they're thinking and some of the responses are indeed correct. Now, before we even give you a problem, we're going to take you through how this would look on a grade paper. And then we're going to ask you if there is any relationship between the subtraction of vectors and addition of vectors. So we wanted to see, based on what we just spoke about, how it look. So here we have vector u. All right. Now we have vector v. We took them from off the grid here and we reproduced them here. But students, we are not adding, this is addition, but we are subtracting. Now, if I wanted to um, reproduce negative v, can you tell me where would it go and what direction? Tell me where would my negative v be or drawn, or where would I actually draw that?
All right. Or let me put it in the terms that they would have learned so
Go
far.
ahead,
So
Mrs. Burrell.
so what would be the inverse vector of vector v here? Tell us where it would go. So we realize that okay, vector b is going downwards, the arrow is pointing downwards. So what will happen with the inverse vector of v? Come on, guys. Talk to us. We want to know what's happening. I realize that you're sending in your coordinates, Shamar, but come on, look at it. Look at our image that we have here. Okay, so Gabriel is saying, Miss, the arrow would now point upward, so it would go in the opposite direction. All right.
Okay, so Miss, I want you also to look at the vector, column vector for v. So if column vector for v is 3, -2, what would be the column vector for negative v?
So Shamar was saying -3, -2. You sure, Shamar? Shamar, you see you're correcting again to say 3 to Shamar. Make up your mind. You're confusing me,
All
Shamar.
right, so probably they want to see me draw the direction. So let us place that there. So we want them to realize that I'm gonna put on my spotlights. And then you notice for the vector v, which is showing the movement in this direction, we're going 3 parallel to the x-axis, and we're going 2 down, which is -2. However, for the inverse vector, we realize that the opposite of +3 would be -3. So we're going 3 units to the left, which is our -3. The opposite of -2 would be +2. So we are going 2 units up. Don't you see that, Mrs. Burrell?
Yes, yes, Miss.
All right. So students, we know you got the math earlier, and I know you saw when we were, you gave us this. You gave us that u plus negative v, but we wanted you to know to see how it would actually look. So though we
Yes.
were given the vector from on the left, we were given 2 free vectors, u and v, and we connect them nicely. If I was to use my spotlight again, Miss, I would have just moved the U up and join it with V. But then when we did the resultant, we realized that we were adding. But what we're looking, or what we want the students to understand, that there is a relationship between subtraction and addition. Students, what is the relationship then? We said it, but we want you to look at the diagram and make sure that though you say it, you see it, and you can say, yes, this is what we mean when we say the relationship. So,
Alia is saying, Miss, they're commutative. Okay. Anybody else wants to add? Let me check our YouTube fans and see what's happening and in the room over by YouTube. Okay, let's see what's happening, YouTubers. All right, so I'm seeing the response from you, Montana. All right. I think that they know what to say,
but they,
but
all right.
they
So,
may be afraid to say, Miss, the
all right.
results, they result in the same answer. So Gabrielle is saying, Miss, the answer would have been the same. All right.
All right. So, students, look at the two resultants. We have when we add u plus v, we have u plus v there. But when we're taking u, the difference, when we're subtracting v from u, we end up with u take v. So what we wanted you to see, just as how we had shared it in the previous slide, that subtracting a vector is the same thing as adding its negative or its inverse, right? So that's what we wanted you to see, that special relationship between subtracting vectors and addition of vectors. So you have two vectors and you want to subtract it. All you simply do is to find the difference by adding the sum of one vector and the inverse of the other vector. All right, we might come a little bit clearer to them, Mrs. Johnson Burrell, if we take them through another problem. So here we have a problem, students, and we now want to see if you're getting what we are saying. You're subtracting vectors. If you have vector A 4, 2 and vector B 1, 3, we want you to show that A take B as an addition of a column of its column vectors. So we want to see if you understand how to show us A take B by addition. What am I adding?
You
I
want to
don't know
try
if,
it, guys?
yes, go ahead.
All right, so Samantha is saying 4 plus -1. Okay, Samantha. All right. You finished, Samantha? Look again, Samantha. All right. So Gregory is now saying it can also be written as A plus -B.
Ba, ba, ba,
Shamar,
ba, ba,
A
ba.
plus -B. Yes, man.
Yes,
The answer's
exactly.
turning up. Yes, guys. Good job.
Exactly. So in other words, this is what we are going to see. So if we're using the addition principle, we're adding the inverse of that vector or the opposite. So vector A plus the inverse of B or the negative of B will give us 4, 2, and we're actually taking 1, 3 from it. And when we take 1, 3 from it, we're left with 3, -1. No, go back for the grid papers. No, man. We want to see how now you can represent these two vectors. So we still want to know, see you use your grid paper, your graph paper to show A take B using the triangle law of vectors. Come student, we want it to be on point. You know, you should have the graph paper right at your fingertip.
I think they're trying it, miss. I think
All
they're trying it,
right.
man. They're trying it. Don't worry, guys. We're almost at the end.
Yeah, we're almost there. Yeah, we're almost there. So don't worry.
You don't worry, man. We're almost there. You have been a great set, both on YouTube as well as Zoom. So don't worry, we're almost there. I'm looking at the finish line, guys. I'm seeing it.
I've seen it too. So let's see if this is what you came up with. You have vector A. Remember, this is a free vector, so we can actually draw it anywhere on our graph paper, on the Cartesian plane or on the grid. So let's check. We are going across 4 up 2, and then we have the vector B, which is 1, 3. Yes, we see the shift 1 unit to the right, up 3 units. All right. However, what do we have here, Mrs. Burrell? Students, did I have A plus B or do I have A plus minus B? What do we have here? Is it a positive B or a negative B? And if it is a negative B, will I need to will I be using this direction or is there another direction that I need to go in?
Right, so I'm seeing TB saying Miss negative B. All right,
So,
so TB change Whoa, Carter, you're on. Yes, Alia, we're going to change it. We're definitely
all
changing the
right, so we're gonna
direction.
change the direction. And you notice that still what we're doing here, we're still moving 1 unit to the left and we're moving down 3 units. So we have our negative B. So let us now complete this triangle because we're trying to complete the show that A take B and we're using the triangle law of vectors to do so. So notice what we have. We are moving along vector A and we are taking vector B from it, and we're seeing the resultant nicely here. All right, students, now that we are through with resultant vectors, subtracting and adding of vectors, here is a question for you. All right, we're winding down quickly now, and even if we are only going to give you like 2 minutes or so to just try and come up with a relationship, and then we're going to talk you through it. So we're now learning how to write vectors in terms of A, B, or A and B. Now the question says, in the triangle ABC, KL and M are midpoints of AB, BC, and CA respectively. Now we have our diagram here that's not drawn to scale, but they gave us some more information. Kame, what else are we seeing on the screen here?
So it's telling us too, guys, that take note, M. So if we look here, M, capital M, is the midpoint of AC. K is the midpoint of AB. And L is the midpoint of BC. So we're given that information as well. We're also given the information that AB, vector AB is 2A, and we're also given the information that vector CA is negative 2B. Click one more time for me, miss. Nice. See there,
Thank you.
guys? So we're given a lot of information here, and now we're asked to determine the first one up, vector BC. So look at where BC is. Tell us, how would you get to BC now? Remember, we would have looked at resultant vector before. So you now need to use what we would have learned to try and figure this one out. And remember, we have to write our answers in terms of common A, common B. So whether we want to say our answer is A plus B or 2A plus B, it still must be in A and B. It must be in terms of AB or A and B. All right, guys? So we're giving you a couple of minutes. I think 1 minute or no, 1 minute sound too enough for them. 60
Enough,
seconds
miss.
is better, don't it? 60 seconds is better.
All right. I see somebody sending an answer already.
Yes, but Tamika, you're sure? Remember, we're trying to find vector B. Miss, is it possible for you to show us with your laser now? So using your laser point. So
So
guys,
we're
look.
looking at
So we're looking at BC.
BC. So we're
Great.
looking at the vector BC. We're moving from B to C. What route can I take to get me from B to C? What are my route? What route can I take? So I want to get from B to C. Yes, somebody telling us. So you know, it's the first they're going to see some of this. So we're still waiting on them to look at it. So what route would I need to take? The one possible route, because there are many routes, but give us some possible routes to take us from B to C. And what do we know already? Okay, some things coming there, miss.
Right. So I'm seeing here that M. Richards is saying BA plus AC. I'm seeing Alia is saying BA is equal to AC is equal to CB. I'm seeing Gregory saying K to B. All right, Paulette, I agree with Vanessa. Let me go back to art. Carter is saying B to L and L to C. Let me go back to what Vanessa would have said. All right. All right, guys, I'm seeing the responses. Gabriel, oh, they're having the responses.
All right. So thank you very much, Mrs. Burrell, and for giving us those responses. So, students, I am looking at what we are given. We are already given the vector AB to be 2A. We are also given the vector CA, which is negative 2B, which means that I would be going from C to A. What would AC be if I'm going from A to C? What would the vector, I will be reading this in the chat. All right. Yes, that would be the opposite of CA. So that would be 2B. All right. So let's look at what, how could we determine BC, the vector BC? All right. So we can determine the vector BC because I did say there are many roots because I did see someone telling us BL and then LC. However, we really don't have any any term for BL. We weren't given anything for BL. So though that was our root, we weren't given any information. So students, when you have the questions, you have to look at what you're given, and from what you're given, we're going to see how we can answer the questions. We are realizing here that we're coming up with a statement that the vector BC can be determined by going to the root BA. Now we already know that AB is 2A. So
Let's see if
the,
they know what
all
vector
right.
BA would be, miss.
Thank you very much, Mrs. Burrell.
So let's see if they can pick up what would be vector BA. So if vector AB is 2A, what would be vector? All right, Tamika, negative 2A. Good job.
All right. So, and they already told me that we were also going in the opposite direction of CA. So AB would be 2B. All right. So let's see what is happening here. All right. So indeed, they gave us negative 2A plus B. Student, is there any way I can simplify this information here, this expression? Yes, I see the answers coming out. All right. Very good. All right. So let's look at what will happen. Somebody said turn it around. Yes. So when I turn it around, we can see 2B take 2A. All right. And when I even further factor it out, we could have been 2B in, so 2 is our factor, and then we could have been left with B take A.
Wait,
Awesome.
yes, miss.
Yes.
And Rohama Cox on YouTube, yes, you were correct, my dear. You were correct. Just seeing it. Yes, dear, you were correct. All right. Yes, miss, you can continue.
All right. What about the vector BL? How could we arrive at BL, students? How could we, in terms of, remember now, we are using in terms of A, B, or A and B. All right. So let's see what is coming up. All
All
right.
right. So Vanessa is saying it would be half of BC. Good observation,
Come on
Vanessa.
now, Vanessa. Vanessa clicking. So clearly we recognize that L is the midpoint then of the vector BC. All right, so nice. So it's a half of BC. Now, who remember when I said something about the factor? Is when we had factored out the two, I'm just going to annotate on the screen here. If we had factor the 2, we would have been left with B, take A. All right. Now, if we had the answer like that and we're now finding a half, when we find a half, because some persons might wonder, Mrs. Burrell Johnson Burrell, where they get B take A from? They're not seeing it, right? So when if we had factored out the
The
2,
two, yes.
right. So when we multiply a half by this, we realize that a half of 2 will give us 1. So that's how they ended up with B take A. Very good. Nice. Love it. And
Good
the
job, guys.
final one is KL. Now, let's look at KL. KL is a little bit tricky, but let's look at KL and see what is happening here. And because of time, we have to go through quickly to get from K to L. If I was to draw a line segment here, yes, we're going from K to L. Can you tell me? Yes, KB.
KBTB. My TB vex with you. Yes,
KTB.
Alia saying I
Ah,
almost missed that. All right, Alia. And
I'm
then
glad I draw it for you then, Alia, because guess what, students? And these are the type of questions sometimes when we have them, we're thinking that they're hard to do, but it's just that we are not able to break the questions apart. So we were looking at what we are given, and then we said, okay, so we're asked to find KL. Though there wasn't a line segment there, I made sure I inserted one, and you saw it. Very good. We know KB. What is KB? We
Come
know
on,
KB.
guys, we know KB. We know AK, so would we know KB? Come on, guys. And do we know B? All right, so Gabriel. All right, Gabriel. All right, Vanessa. So Vanessa A. Amanda. All right, Amanda. You're sure, Amanda? Double check that response for us.
So
Carter,
we are
you're
saying that this
sure?
is A because the entire thing is 2A. We
Yes.
just found BL. BL is what? B take A. So they can combine everything together nicely. All right, students, we like where you're going. All right, so I'm going to clear my screen because I have it all together on in my next. All right, I'll take you over to the next slide after.
So here it goes, guys. So A plus B minus A. And we know what we would end up with here, right, guys?
What? Ask them for me. Not, yes, I want to hear what they think would
All
end
right.
up with.
So tell me, all right. So TB, Tamika, Gabriel, you're sure? Double check that one for me, Gabriel. All right. So TB, Tamika, you're on. All right, Gabriel. Good. Yes. Davia, great. Good job. So they're saying right here now, A plus B minus A would evidently leave us with B.
All right, very good student. Great job. We're proud of how you would have looked at the question. At first you were hesitant, but guess what? You started to break it apart. Look at what you are given. What do you notice? What can I do? Do a little bit of trial and error. So we want you to become familiar with working vector problems, especially in terms of the vector using the algebra part of vectors. All right, so earlier we would have done some of this. No, is there a relationship? Yes. And I want to just to go through quickly that yes, there's a relationship between K and L. No, K, L. So we want to look at the vector KL. I'm going to animate it again. And what words have we looked at when we were talking about relationship earlier? Remember, students, when we were talking about relationship, so we are looking at KL and we're also now looking at AC.
All right, so Alia,
Let me use a
TB,
different
Vanessa, Miss,
color.
they're popping, they're Davia. Wow,
Mm-hmm.
they are popping, they're saying parallel, Miss. Parallel. You're sure, guys? You're double sure? You're triple sure, guys? Think about it. Davia is saying scalar multiples.
All right, so we are seeing that KB is B. Can we just work that? We were told that CA, which is going in the opposite direction, was minus 2B. So if we're looking at AC, thank you. If we're looking at AC, we'll realize now that is 2B. Now, can we realize or are we seeing that KL is a half of AC or AC is 2 times that of KL? So students, we just wanted to show you that we have been speaking a lot about relationship, and those are some of the things we want to get you to see. So Miss, you know where we're at? We're at fun time. We're actually in the very last part of the slide, students. So just hold on, hold on. We're gonna finish soon, man. Don't shake up yourself. Run and get some water and come back if you're at home, and move with the phone and stuff and run, come back. So we're continuing, Miss, about collinear vectors. Miss, when we talk about collinear, or before we even go into that, I have an image here. Let us have a little conversation, students, about what we have here. What are you seeing? What do
Well,
you
based on what
notice?
I'm seeing, I'm realizing that we have a sun, we
Mm-hmm.
have the earth, we have a moon, And when I look carefully, I'm realizing that all of them have something in common and all of them are also sitting here. I'm looking at an imaginary line in my mind right now. I hope I'm not getting mad, but I'm seeing an imaginary. Oh, Gabriel is seeing the line as well. So it's not me alone getting. Thank you, Gabriel. So
All
Gabriel is
right.
also helping me to say they are all in lines. All right, Gabriel.
So they're
Thank you.
all, so what they have in common is that they're all in a straight line. All right, nice. So, sometimes we hear about the solar eclipse and we go outside and we try to wait up for it and or see it. And they say you have to put on dark glasses because, all manner of things. But guess what? This is a time when the sun, the moon, and the earth line up with the moon being in the middle, the common point. Now, who would have thought that space, could share so many things about vectors? So, this notion, Mrs. Johnson Burrell, about, how them going to use vectors, that is outside of the window, they are seeing it now in real life. You get what I'm saying? So students,
Yes.
we're going to get straight into it because we're in the last leg. We're in the final part of the workshop, and you have done great. I'm so proud of them, Miss. All right, so let's look at this. So we're looking at an activity. So take us through this one, Mrs. Burrell, if you can.
All right. So so they say in common direction, common point, quality saying on the same path. So here we're given 3 points. We're given P, Q, and R. Now P, the points of P are 1, 1, Q, 2, 2, and R, 4, 4. And we're asked to plot the points. So here Mrs. plotting the points for us. Thank God. So Mrs. plotting the points for us on our Cartesian plane here. And remember, it's our Cartesian plane. We have our y-axis and we labeled our x-axis. Now, the next thing that we're asked to do is to join the points P, Q, and R. So this is what we want you to tell us, guys. We would have shared it just now, but just so that we sure you clear on it, what are you observing here about all 3 points? Come on, guys, what you observing? So tell us, what have you observed? What are you seeing here coming out? So you're looking at the 3 points, P, Q, and R, and what are you noticing?
All right. So thank you for that, Mrs. Johnson Borrell. So we have the 3 points. And yes, what are you noticing? So let us see what some persons, oh, yes, it's a straight line. Yes, they're in a straight line. All right. They are all in a straight line. All right. Excellent. So what if I had removed the point R? Would P and Q form a straight line? Would these 2 points give me all right, yes. No. With with collinear points, because you notice that we started this section by labeling it. So this is something that I needed to understand. You may see this word in some of the vector problems that you are getting, or if you're practicing in your past papers. So here's what we are saying, that collinear points are points that all lie in the same line. So whether they are close together or far apart, or from a real line segment or a line. So just like how we had how the earth, the moon, and the sun was aligning for the eclipse, we were looking at the line itself. We noticed that there was a common point. Now, what would be the common point here for these 3 points? Which point here is the common point?
All right, so Vanessa is saying Q, Gregory Q, Gabriel Q.
All right, so very good. So keen observation. So this is the thing. We are allowing you to build your observation skills. So when you're doing the questions and you're practicing, you're going to now start turning your eyes to say, what is it that I'm observing? What can I pull? You know, you're asking yourselves those questions. So very good. So collinear points are points that lie on the same line. They don't have to be close. They can be apart. But in order to check for collinearity, there must be a common point. All right. Let's see what else we can take them through before we finish this session. So we are now going to try and determine the column vector. So we already have exhausted how to arrive at the column vectors. What would be the column vectors, students, for PQ and QR?
I hope they were paying attention earlier because we would have shared a part of it. So we hope they were listening. Come on, guys, look at it. What would be the column vectors? Miss would have asked of P, Q, and so it's vector PQ and vector QR. All right, Gabrielle, I'm seeing your response. So Gabriel, I think you may have wanted to write that you're talking about PQ. Is it that you're talking about PQ, Gabriel? All right, TB. Which one are you talking about, TB? All right, Vanessa is saying PQ is 1, 1, while QR is 2, 2. All right. Let's take a look, miss. Let's take a look. I think
All
that they're on the
right.
right ball. So let's take a look.
Okay. So now, who remember when we were talking about parallel vectors? And one of the things we said about parallel vector is that one is a factor or multiple of the other. We were looking at that. Now, for most of you, you would have seen where, because some persons use statement like the lines never meet and all of that. But just for food for thought, now here we have two vectors, PQ, which is 1, 1, and QR, which is 2, 2. What if the distance apart is 0? Just think about it, because I want us to understand something now, how it is that we test for collinearity. So here we have the vector PQ, which is 1, 1, and the vector QR, which is 2, 2. What can we say about the vector PQ and the vector QR in terms of size? Go
All right,
ahead.
so Gabrielle is saying they share a point. Aliyah, they have the same scale factor. All right. Vanessa is saying QR equals 2 PQ. So vector QR equals 2 times vector PQ. And Gregory would have agreed with Vanessa. Gabrielle is also saying vector PQ is half of vector QR.
All right. So I like the statement that someone made earlier that there is a common point Q. Very good. I'm also loving the fact that one person either shared that QR is twice the vector PQ, or PQ, the vector PQ is half that of QR. So here's some points we want you to note, students. Now, since PQ and R are collinear, now state the condition. We're going to now be looking at some conditions. We're going to test the conditions to speak whether or not they are collinear. So state one condition for collinearity guided by the relationship of vector Q, PQ, and vector QR based on what we just discussed. One, they must have a common point. So if we're going to be looking at 3 points, if they're collinear, we must test to see if that those 3 points have a common, a point that is common to all of them, just as though we're pointing out Q here. All right. The next thing we want to look at when we are comparing the magnitude or the vector, column vector, we're going to check to see if it is a factor or a multiple of it. So we first want you to understand when we are saying that we're going to test for the collinearity of points. All right. So first we want you to understand that. So having spoken about this, and some of us are saying yes, they're agreeing with what we are saying. Now let's look at the same question. We are giving you the same question. We're going to take you through this question and then one last question, and that will be it. So we want you now to express vector PQ in terms of Q, R, and state your observation. We just said it in words, but we want to now use U and V to express it, or we want to speak of it in terms of PQ and QR. So earlier somebody pointed out that one is a half of the other. But the challenge you have as students sometimes is, how do I write what I'm saying? You know, so I think that's where some of us might, you're saying it, but you're not sure how to write it. So let's look. If the vector PQ is equal to U and the vector QR is equal to V, you just told me that, you notice my red arrow is just popping, that QR is 2 times that of PQ, or we can say that PQ is half that of QR. So we're learning now how to express what we just said in words. So we had the vector PQ, you gave me the column vector 1, 1 for PQ, and you gave us the column vector for QR as 2, 2. Now the question simply asks us to express PQ in terms of QR, and that's the final statement that we have on the board, on the screen right here. So we have the vector Q and PQ is actually equal to a half of the vector QR. How would you now write it if I say to you, express QR in terms of PQ? What would you now write? I am now asking you to express, yes.
All right, I'm seeing the responses. V equals 2U, QR equals 2PQ. All right. QR equals 2P. So vector QR equals vector 2PQ. All right.
All right. So, all right. So I'm loving that. So just writing what they said. So they're saying the vector QR would be equal to what? 2 times.
It's 2 times vector PQ.
All right. So that is how we're asking when we're expressing it. So students, we want you to become comfortable, you know, with reading the vector, be good at reading the vector language, or to write it, you know, not just say it in words, but what does it look like? Because you are saying to us QR is equal to 2 times the length of PQ, but how would I write that as it relates to of expressing it in vector language? And we're learning how to do so this afternoon. So I must commend us. All right, we have to move along. All right, we're
But in
going on
moving
nicely.
along, yes, in moving along. So we're just pointing these things out, which we would have already shared. So
Right,
we're
so let
just
them write it
pointing these
down.
things. Yes. So write it down, guys, or do a screenshot, whichever one you prefer, because we would have already spoken about these. We just want you to see it for yourself. And after this, we're just going to be looking at ratio and collinearity. That's all we're looking at after this, and then that's it. Okay, guys? So don't worry. We are almost there. I know that we said, but guys, come on. We can't just leave it like this. We're just wrapping up. All right. So have we finished taking down our notes, guys? Finished taking down our notes? Tell us if we're finished. So I'll read it. When proving that two vectors are collinear, we need to, one, show that one vector is a multiple of another, which I would have seen, and we would have seen it and heard it from you earlier. Two, show that the vectors have a common point, and Vanessa would have shared it in the chat. She even wrote it in full caps that they must have a common point. So in order to do so, we can factorize by a scalar quantity or a common factor. We have
All
something
right.
else to add to this, Miss? Yes, ma'am.
Yes. So we are
Good.
giving
So
them an example now. So you can
which
take
they
them
know
through.
already. Yes, man,
Right.
they know already. So we're given these two and we know it, guys. And we can show it that, well, in looking at this two, we can see that, all right. So one vector is a multiple of the other vector, right? We're seeing it here. So from this, we can see that vector AB is a factor of vector BC, or vector BC is a multiple of vector AB. So 4AB, so it's 4 times vector AB is equal to vector BC. All right,
Awesome.
guys.
All right, we're on the last lap. Now, this is the
Yes.
very last question. So we're now looking at vectors in terms of ratio and the collinearity. So we have a parallelogram OACB. So it's a parallelogram, and the vector OA is equal to A and the vector OB is equal to B. Now, which vectors are parallel and equal? Can you tell us which vectors are parallel and equal? We're hoping to wrap up in the next 10-15 minutes or so.
Oh, all right, Paulette. So Paulette is saying, could I get a screenshot? All right, Paulette, we're going to go back for just 30 seconds. Miss, is it possible for you to just click back? 30 seconds. Let Paulette, Norman, continue. So bring Norman, the next one. Right, and there, right there. So Paulette, go ahead, quick, Claudette, Paulette, 30 seconds, 30 seconds, guys. Just bear with us. 30 seconds, all right? 30 seconds. Paulette, you finished doing your screenshot? Let me know, Paulette. Waiting on you. We're not leaving any soldier behind, or we would call them soldier. So we're not leaving anybody behind. Ready, Paulette? All right, got it. Good. So we can go back now, Miss. Nice. So we're still on our ratio and collinear. And Miss would have asked you which vectors are parallel. And we got this. We know this. All right. So
All
Gabriel
right.
OB and OA, nice. Vanessa B's, all right, good. So we know this, guys. So we're just looking at it to look at the full activity in its entirety, because this is the tip of the activity, but we just want to check that you're following us. All right, Miss, you can continue.
All right, so here it is now. We're exploring the ratio concept. So sometimes in the question, the CSEC questions, you'll probably see that you're given a ratio in terms of the magnitude, and you're wondering, how would I work this? So here it is. So if the line OB is extended such that OB, the vector OB to the vector OD is in the ratio 1 to 3. So you see earlier my line, they kind of look off, but it slide nicely. I'm using the animation. So I'm extending the line to the ratio 1 to 3. So here, if we're talking about ratio, it's saying that OB is 1 to 3. All right, can anybody tell me anything that they observe? If not, we're just going to go through, because we are down to the wire and we want to make sure that you get everything. All right. So what is the relationship between the length of OB and OD? Can anybody tell us? Look at what is going to happen to my animation. So if I pull this apart, so this is my new length OD, and I now want to compare it with OB and BD.
All right, so Gabriel is saying OD is 3 times OB. Three
Gabriel
times.
Brightman.
Gregory saying 3 times OB. Watch here. Davia switch things around for us and say, I'm not following anybody. I'm going to be a trendsetter. So OB is equal to 1/3 of OD. Oh my God. Okay, guys.
So students, it also is dependent on how you are reading the relationship. So if I'm given that OB is B, then BD becomes 2B, all right? So we can say that OD is 3 times OB, or we can go and say that OB is 1/3 of of BD or
OD.
OD.
Yes.
Thank you.
Yes.
So students, it doesn't matter the way in which we express, but when we are expressing, we have to make sure that we're talking about the right things. If we're talking in terms of OB, we'll use the 1/3. If we're talking in terms of OD, we'll use the 3 times B. You're doing nicely. So I don't want us to be alarmed or afraid of the very ratio in the concept. All right. So you'd have done ratio a very long, probably in the lower grades. However, if it is we're comparing the information to 1 to 3, we'll realize that it's 3 parts that we have. So I want to bring that out as well because I don't want anybody to go and add. Because you know me, sometimes there's this tendency when we see ratio, we go find total and we add and we get 4, but we just want them to realize that the ratio here and it's really 3 parts. One is B and the other one is 2 times B. So that's the ratio what it is. All right. So we also, someone shared this. So we are still exploring the ratio concept. So if the vector xc, no, but Miss won't have the x on this yet.
Not at
Clearly, I need
all.
to put in an x somewhere. So listen
Yes.
now. If xc is 1/3 BC, all right, so XC is 1/3 BC. First of all, how many parts would BC be split into if I from based on that statement? I'm seeing it
Right. So
lighting up.
Vanessa is saying 3 parts. Gregory is saying 3. All
Awesome.
right.
Very good. So where would you place your X?
Tell us, guys, where would you place the X?
Is it closer to B or would it be closer to C? Because if XC is 1/3 BX.
Closer to B. Okay. Closer to C. All right. Closer to C. So somewhere on the B wagon and somewhere on the C wagon. We're going to show you who is
All
correct now.
right. So that's where we would place our x. Because remember now we're saying the vector xc is 1/3 the vector bc. So clearly 1/3. And why do we have a is because we already spoke about parallel sides. So we know that OA, the vector OA and the vector BC, they're parallel. So if they're parallel and they're equal, it means that if this vector here is 2a, then this vector would also be. So if this is a here and the whole thing is a, then it would work out to be like that. So,
Yes,
all
yes.
right.
And our next slide is even going to help them to really have a better picture too we're going to be adding something else. So we're going to show you where X is really on it, and you're going to see something else as well, guys, when we move on to our next slide. So yes, we have this here, but you're going to see it a little bit clearer when we add something else to this question.
I also want them to realize that the A for OA should be probably to the middle, probably because it's at the left. You might have some person thinking that it's not for the entire length, but it's coming from the previous question, so it's the entire length. So notice here, so what am I pulling? If they told us that XC is 1/3 A, then in order for us to get a whole, then BX has to be 2/3 A. All right, so that's how we would end up back with 1, because 1/3 plus 2/3 will give us the whole, and that is what OA is. So OA is actually 1A. All right, so we're moving on and we want you to see something else. So what route would you take for the vector AD? No, if I want to go from A to D, you notice I bring up some things, yes, because we are down at the wire and we want to make sure that you take a screenshot of everything to get from A to D. Mrs. Burrell, how would
Yeah.
we go? We could use the root what? As you
Well,
can see.
see right here, we're looking at vector OAO, sorry, plus vector OB plus vector BD.
All
And
right.
we're also looking to see that which is the same as vector AD is equal to 3B minus A. So
But
Mrs.
before, yes, so
Yes,
I
yes,
have that
Miss.
as an answer, but how did I arrive at 3B take A? Let us look at that. So how did we come up with AD being that answer? All right, look at it. We know that the vector AD is moving from A to O, which we know it's in a negative direction, so that is minus A. What did we learned earlier about OD? OD would be OB plus BD. That's how the students remember earlier when we were extending the line is the same extension based on the ratio that we were given. So we are showing you that OB is B. We extended it, we had it in the ratio, and now we are identifying the 2B. So students, when we simplify the expression that is highlighted here, when we have 1B plus 2B, what are we left with?
Come on, guys. Don't tell me that we fall asleep. All right, so we're left with, come on. All right, so when you simplify B plus 2B, yes, we have 3B, but what would be our entire expression now? So put it together for us now. What would be our 3B minus A? All right,
All right, but
nice.
before we get there, we would simplify, and some of you can just jump from this second line all the way to this final answer. But I wanted you to realize that we have minus A plus 3B, which is the same as 3B take A. Now, how did we arrive at this? All we did was to just look at the diagram, look at the possible roots. Now, is there another route that we can take? And would the result change? Now, let's look. How else could we go from A to D? Hmm?
All right, so Vanessa is saying vector AC plus vector CB plus vector BD. All right,
All
interesting.
right, and that just came up because we are down to the wire, students, and we want to make sure that we get in the last 3 slides. We'll have a post test for you, but what we're going to do is allow those who are on YouTube to scan the barcode, or we'll look at the link, and you can probably use the link to answer the questions, because we want to check how much you would have learned today, and we also wanted to evaluate the session. So don't log off. We're getting down to the wire. So earlier, I believe Mrs. Johnsborough shared that someone said that we could have gone the route AC. Let me put on my spotlight. So we could have moved from the vector for AC, we could have moved from A to C, yes, which we know is B because it's parallel to OB. Then we would have moved from C to B, right, which is in the opposite direction. All right, so we know that this would be what? Negative A. All right, and then we're going from B to D, which is 2B. And when we simplify the terms, we realize that we end with the same results. So if we had taken the root AO to OD, breaking off the little small roots, or AC to then CB, then to BD, we'd end up back with the same root. All right. Screenshots, because we want to move quickly into the next question. So let us.
Screenshot for us, guys. Screenshot, because the next question, it's just that we're adding a little bit to this one, still looking at collinear, and we're looking at the vectors being parallel, as well as what Vanessa would have clearly highlighted earlier of us sharing a common point. So that's basically what we're doing next to just prove collinearity. All right, guys? So hurry up
Just
and do your
making sure that they
screenshot
get
quickly.
it.
Yes, yes, miss. So screenshot
All right. If anything, we can come back to it if you want for us to allow you to take a screenshot. All right. So let's move on. So now we're looking at the two final things. So we're proving that the points, these are the points that we're proving. We're proving that A, X, and D, that they all have a common point. What do you think the common point for A, X, and D is? What is the common point?
X.
All
All right.
right, very good.
X,
So we are
X.
proving now that they have a common point. This is how we are going to guide you through the proof. So this is how we prove. One, we're going to prove that the vectors are parallel. So make sure you write this down. We are also going to prove that they have a common point. All right, so let's look at that. So we have the vector AX. Let's see how we can work AX quickly. And let's look at XD. Can you tell us how we would arrive at AX and XD? All right. So yes, AX, let's go to my spotlight here. So we are moving from A to X. Yes. And we can go from A to C and from C to X. Yes, because we know what AC is. That would be what? That would be B. But if we are going from C to X, we'd be going in the opposite direction. So that becomes what? Minus 3A. Very good. Let's see if that's what we have here, Mrs. Johnson Burrell.
Yes, yes. Let's take a quick look.
All right. And remember now, because of how we were looking at the triangle law and we were adding, we realized that when we're adding minus 1/3 A is the same thing as saying B
Yes.
take. Now, how did I get A divided by 3? How that come up now? We want you to realize that this 1/3.
Negative a third A is the same as minus A. So B plus negative a third A is the same as saying B minus A thirds. All right, guys. So
All
in fractions,
right.
a third A is the same as A thirds. Fraction, guys.
All right, very good. So thank you for that. So we have just now looked at AX. Remember, now we're testing whether or not they're parallel, and we're also checking to see if there's a common point. We already established the common point to be X. So let's look at XD.
All right, so
Oh.
Davia would have quickly told us that vector XD equals vector XB plus vector BD. Good job, Davia.
And do we have the vector XB? Yes.
Yes, we
Are we
do.
going in the right direction? Are we going in the opposite direction?
Anybody? Come on, guys. Which direction? Opposite. Good job.
All
Good job,
right, so
guys.
therefore we would end up with the vector XD is equal to negative 2/3 A plus 2B. All right, and we can rearrange this. We can make this, we can turn it around so we can have 2B take 2/3 A. Now, if I was to factor 2 out of this, you notice we have been using the word factors and multiples. When I factorize here, I'm factoring the 2, which means that if I was to expand, I should get back the same thing highlighted here. All right, so when we factor it out, what kind of relationship, what do you notice about AX and XD based on the what we have worked out here?
Come on, guys. Come on. Let's see what our YouTube fans are saying. All
They get
right.
quiet, man. Oh, we're not hearing anything from YouTube. It's been a while.
Oh, man, they have been responding, man, and I've been responding to them as well. All right, so Davia is saying here on Zoom, scalar multiples.
Okay. All right. So, all right. So here's scalar multiple, but I want something more. Comparing AX. AX, the vector AX is B take A thirds or 1/3 A. And then the vector XD is 2 times B take A thirds or 1/3 A. What kind of relationship, man? Come on, we don't know the
All
wire, you know, we
right.
don't know the wire,
So,
man.
so Vanessa, Gregory, Gabriel are all saying a vector AX is equal to half of vector XD.
All right, and I will take that, or we can say when we compare them like that, it's 2 times. So XD is 2 times that of the vector AX.
Yes,
So
so
you
they're
see
still
how
correct. Yes, they're still correct. It's how they would have done their comparison.
Exactly. So you see, students, all we did, we just take it apart in chunks, in bits, and we just try and put it together. So, nobody have to fear this topic. Once you take it apart like this, miss, you notice, and they're
Yes.
enjoying themselves. All right. So proving now, proving the collinearity. So proving that they share a common point. So as what I've said, that X was the common point. Now let us see if this is true. We have to always show that something is true. So we are going to prove that the common point exists, that the entire thing. So we're going to prove that AX plus XD is equal to the entire length of the line segment, or the line here, AD. That is what we're going to prove. So, students, when I say that we're going to prove to hold if something is true, we're going to see if this statement is balanced. Did we have AX? Did we have AX earlier? Yes, we work out AX already,
X, yes, yes, miss.
And we work out AX already. And we also know that AD is equal to 3B take A. So let's combine them now. So we have AX, which is B take A thirds. Students, I
Yes.
wanted to see something. You notice how each part of the question supports the other part. So when you work a problem, something, some information, so go and look back and see if the information that I worked in a previous part of the question can help to support how I work the other parts of the questions. Sometimes they are related and they intertwine and they will help you. So we already worked AX. We also calculated XD in the previous thing. Now, all of this not look so nice, miss. It look rough. But let's look at what we have. We are proving that all of this on the left, that the vector AX plus the vector XD is equal to the vector AD. Now look at what we have. Let us look at the B's. You notice, miss, that B plus
It's
2B
common, yes.
is
And
equal to 3B. So that work
yes.
out. But Lord, miss,
We
this
need to
one
tidy
third
up the
A.
fractions. Yes, man, we tidy
Yes.
up.
So this one third A. So we have minus a third A, and we're taking 2/3 A from that. All right, we're adding two fractions. We have negative a third plus negative 2/3. That should give us -1. So you realize how the pencil out, and therefore the two sides are equal, which means indeed there is a common point. So it holds true that there is a common point for A, X, and D, and that is indeed X. All right. So students, we're at the wrap up section, but we want to hear from you. We can open our cameras now, miss. I think they can see our faces. No, we're unable to see yours, but we want to say to you, let us see how much you have learned. Now, in the chat, we are going to place the link, and we're going to give the students about 10 minutes or so to actually work some questions that we created in the link for the students
So
who,
I would have sent the link in the chat, guys. The link is sent in the chat of the post test. So we're giving you around 10 minutes to do the post test. I'm also wondering if I should share the evaluation form link as well, just in case they want to maybe do the test outside of the
yes,
session. So I am also going to share the evaluation link as well, guys. And we want you to evaluate our session. So we want you to evaluate our session. So I'm going to be sharing the all right, no problem, Afaya. And in you doing the evaluation form, I'm going to be typing our names in the chat because you're going to be evaluating the session. So that is one presenter. And this is your next presenter. So let me now copy the link for the evaluation form, and we're asking you to complete the evaluation form. That's okay, Barnes. That's fine. That's really okay. Still evaluate what you would have seen or what you would have learned so far from the session. So guys, even if you were late, what you can do is just screenshot and you'll see both our names there in the chat, and you just click on the link. So you know when you go to the chat, you're going to look for both Mrs. Cameron Edwards and Mrs. Johnson Burrell. You may have to do it 2 times, maybe that may happen, but still evaluate this session. All right. We also sent the link to your post tests as well. So for those who are on YouTube, you can go ahead and scan this barcode right here and evaluate the session as well for our YouTube fans. We want to thank Antonio. We just brought it up. So look and see if you are, so Antonio on YouTube, you're not seeing it. All right, so hang on, you may soon see the barcode. So we really want to thank our YouTube fans, and we want to thank our Zoom fans. We want to thank all of you students who are sticking with us to the end. You have been great. You have been marvelous. And for those who saw me earlier, yippee, Shamar is still here. Shamar, you're still here. Yes. See there, Shamar? Yippee, hooray. Yes, Vanessa, we had fun. We enjoyed our time with you all. Yes, and we're happy that you're all commenting that it was a great session. Please go and evaluate the session, guys. Okay, Shamar? Okay, Vanessa? Click on the link, evaluate our session. All right, Gregory?
Mrs. Burrell, we want to also encourage them to join us for the remaining 6 other workshops, the vectors, the circle theorem.
Not vectors, miss. Really? I see that Shamar rubbing off on you, and Gregory as well,
It's matrices, right?
Matrices we're having on Thursday.
Circle theorem, linear programming. So students, we are hopeful, happy that you participated. You'd have registered for the other sessions. Stay tuned. They're gonna be just as exciting.
All right, guys, just as exciting as this session. So how many persons did their evaluation form? Let me see if all of you just sitting down laughing at us, smiling with all of you. I don't see anybody type in the chat that means I finished, what's happening? You just completed the form. Which one, Gabriel? The evaluation or the
post test?
The post test. Which one, Gabriel? The evaluation, okay. You had to do 2 for both Mrs. Edwards and Mrs. Burrell, or you had to do 1? Okay, all right.
All right, so.
Okay. So Gabriel did 1. What about the others? Come on, guys. All right, that's fine, Paulette. All right, so guys, it was really great having you. As we said earlier, we really want to tell you that we appreciate you, both our YouTubers as well as our Zoomers. Okay, guys? Remember, we have 6 other sessions. The next one will be on Thursday, not tomorrow, but the day after tomorrow. The day after tomorrow is Thursday, right? Yes. So tomorrow is Wednesday, so it's the day after tomorrow. And we'll be looking at matrices. So be here, be on time. Remember, we start at 3.
Math fun.
Yes.
Math counts.
So you're all free to go now, guys. Take care. Ta-ta. Toodles.